All right, welcome to Chapter 6. We're only going to do a couple of sections here because that's all we have time for this semester. We are dealing with applications of the integral. Now we're actually going to use this thing to compute interesting results. Let's just say we're solving interesting problems. Okay, this first section, well, okay, it's more geometrical than anything, but it has its implications. It truly does. What it is we're going to find the area within of a region that is bounded by given curves. It could be more than one curve. It could be 3 or 4 curves. And yet we're going to use our knowledge of Riemann sums and to set up the integral for each of these problems, okay? All right, so the whole thing is basically, are we able to come up with the area between curves? How do we develop it? And how do we choose the variable over which to integrate? Now, in this section, we don't just always, this is interesting, it's a big step for you guys coming up. We don't always integrate with respect to x. There will be times where it makes more sense to actually have our Riemann sums, our rectangles, be sideways. We'll get to that. Let's look at this one. So consider the area between these two curves here. F of x is y squared, and the g of x is the square root of x. And I took the liberty of going to Desmos and graphing these guys, and there's what they look like. Okay, basically we want to calculate the area that's between these two curves. Okay, so here's the story. What we want to do, let's do this in red, I think. This color here. What we want to do is slice and dice this thing into mini rectangles, but as you do so, the heights or the lengths of the rectangles are bounded below by the lower curve and above by the upper curve. Can you see that? Okay, and as you go out here, of course, these guys meet at the point 1, 1, all right? Imagine it just being the blue curve. Then you'd go, oh, just integrate, the following. If it was just the blue curve, you'd go, the area is the integral from 0 to 1 of the square root function. Yay! But if you did that, you'd go, okay, I'm going to pick this like little interval, and I'm going to let x sub I star be plugged into this function. The height of your rectangle would be all the way there. You don't want that because you want the area between the curves. So you end up, how do you do that, I wonder? Well, this guy right there, if this is x sub I star, okay, then this height here is the square of x sub I. Let me write that better. It's going to be x sub I star, but the lower red curve is the squaring curve. If you went all the way up to the top, let's say we're the same x, then that height would be the square root of x sub I star. So how do I get just this distance here? From here to here, because that's how tall that rectangle is between the curves, okay? You take the difference. That's right. You take the difference. You just go, what we say in calculus a lot, take the top curve minus the bottom curve. That's exactly right. And that is absolutely correctly set up. When I take the y value of the blue curve minus the y value of the red curve, I find the difference between them, which is this gap between them, and that's what we want. The height of each rectangle in the Riemann sum, I want it to be that height, okay? All right, so always think of it that way. You can say the area, oftentimes, is integral a to b top curve minus bottom curve dx. But what if it's a curve that's facing like this way and you have x as a function of y? Well, we'll get to that in a little bit, but you ought to think about that. Think about it differently. The top curve is no longer the top curve. The top curve is the bigger curve, or the one that's farther to the right. So really maybe we should make this effort and go the larger function. How about that? Minus the smaller function. If we were writing a book, I might be your editor and say, why don't you write that instead? And you go, well, I'm going to write both. I want them to understand this, to really understand this. So it's clear that the square root function, the blue curve, is above the square function. So we're going to go ahead and attack this problem down here, and we'll just integrate. We just go, well, okay, x to the 1/2 power gives us x to the 3/2. It's 2/3 x to the 3/2 power, because this is x to the 1/2 power. And then minus 1/3 x cubed from 0 to 1. So you end up plugging in 1, you get 2/3 times 1 minus 1/3 times 1. And then when you plug in 0, you get 0. And you get 2/3 minus 1/3, and the area is 1/3 of a square unit of area. That's it. That's it. Okay, so what am I pausing for? You can pause if you want and rewind it or whatever. Let's go to these problems. I think I have 1, 2, and 3, and 4. Let's see if we can fit them into one video, if you don't mind. Find the area bounded by, we can make it 2 videos if you want to. Find the area bounded by the parabolas x squared plus 1 and g of x is 3 minus x squared. Okay. Okay, so, hey, we got to know a little bit of graphing, goes a long way. You know that this is a parabola. It's opening up because it's positive, but this is a parabola opening down. So we may or may not know how these guys graph. If we did, that's just x squared lifted up 1, and he's doing this number. The other guy's x squared going downward, but lifted up 3 and going down like that. So what we want then is the area between these guys. And so therefore, I can tell you that the area is equal to the integral. The upper curve, or the larger curve, is really 3 minus x squared. Do you see that? I graphed it pretty quick. The lower curve is the one that goes x squared plus 1. The only thing that's missing, and this is what this is a good lesson for, is, hey, what are the limits of integration? I need to know to integrate from where to where. Some of you can kind of guess it, but we don't guess in math. We don't do that. Instead, we take these two functions and we find out where they're equal to each other. So in other words, we go, how about we set x squared plus 1 equal to 3 minus x squared and solve for x this way? Because when we set the y values equal to it, we're saying, where are the y values equal? Because if you find that, boom, this is like the substitution method. Y equals this, y equals that, set y equal to each other, and away you go. And this is not a hard one. You go 2x squared is equal to 2, so x squared is equal to 1, so x itself is plus or minus 1. That is right. If you guessed it, you got it. So from minus 1 to plus 1. Now listen, that's what you would integrate for your answer. And I may not even, I forgot. No, I'm good. I may or may not do the problem. I just want you to see the setup because you guys are getting better and better. Hopefully you're practicing and you're doing your definite integrals because all you're going to do here is combine terms, integrate, and apply the limits. Okay, let's do it. Let's do this one together. So we've got, therefore, the area is the integral from minus 1 to 1. Let's see what we've got. We've got 3 minus x squared minus 1. Okay. Oops, where'd I go? There I am. So so then we go equals integral minus 1 to 1. It looks like we've got 2 minus 2x squared. It's time to integrate. 2x minus 2/3 x cubed from minus 1 to 1. This is where smart calculus teachers and students go, oh, it's an odd function. Oh, it's an even function. Things happen. I didn't really get into that with you guys. I just say, go ahead and calculate it and find out through experience. When I plug in 1, I got, let's see, 2 minus 2/3, right? Because I plug in 1, I get 1 cubed is just 1 still. But then I go minus, and now I'm going to plug in negative 1. So I'm going to get a minus 2. And this minus 1 cubed is negative, but another negative makes it plus 2/3. And look what's happening. This thing doubles up. It's equal to 2 minus 2/3 plus 2 minus 2/3 again. So it's really the same result. Look, I'll wrap it up. It's the same result twice. So you get 4 minus 4/3. Okay. 12 minus 4 is, I think we're getting, in this case, 8/3. Okay. Pretty cool. A person who really knows this, hey man, it's an odd function. All you have to do is the first one and double it. Okay, well, we have enough on our plate. But if you want to remember that, that's a cool thing to know. From being a teacher, I look at it coming and I go, yeah, yeah, yeah. But here's another thing that's really cool. You can also use symmetry. Symmetry means if you look at the curve, let's draw it up here again. He's doing this little number like that. He's doing this thing like that. And you're trying to find the area between those curves. What you realize is this half area here is identical to this half. So by symmetry, the idea is all I have to do is really calculate 1/2 and double it. We can say the area is equal to the integral, say, look, you ready? From 0 to 1, that'll do this half here. And it'll be the same thing. It'll be 3 minus x squared minus x squared plus 1. Same thing, but then you double it because you have 2 halves. And they're symmetric, okay? And that takes care of it, and you know you're going to get the same answer. So if you're feeling like, yeah, I don't know, man, is this going to work or not? Yeah, you can basically look at the curves and go, you know what, parabolas are perfectly symmetric. So the better you are at that, the better you're going to be at this thing, at this particular section. Here's another one, the area bounded by these two curves, and let's see what's going on here. This guy, if I want to see what he's doing, he's looking like the square root function, but he's shifted 1 to the right. So that curve is like, here's 1. He's doing that number. This one's weird. It says x minus y equals. Why are you being sneaky with me? Really what that's saying is x is equal to, say, y plus 1. So why don't we say y is equal to x minus 1? You see that? I kind of had to do that, huh? So x is equal to y minus 1, he's down here, and then I think he hits here, and I don't know where they meet, but I think we're talking about a little sliver of area between them right there somehow. Okay? So you might be interested in figuring out what the limits are, but you can see what the upper limit is. It's the square root function. So a person in a hurry would say the area is the integral from I don't know, but it's going to be the square root of x minus 1 minus the line, which is x minus 1 dx, like that. This is a good challenging area for you guys. I kind of go through this and I go, oh, it's easy. And then students are like, whoa, because you guys have not really applied the integral before. Someone just said integrate, and you just integrate. We have had the experience of area under curve, but now we have a bottom curve, if you will, and you got to kind of work a little harder for the answer. To find out where they meet, we just take these two guys typically and go square root of x minus 1. When is that equal to x minus 1? You can kind of guess if x is 0. Does that work? No, you can't plug in 0. We better solve it. So I'm going to square both sides and get x minus 1 is x squared minus 2x plus 1. And I'm solving a quadratic, so x squared, what, minus 3x plus 2. Oh, it's different. Okay, so you see how important this is? It is x minus 1 and x minus 2. Aha. They meet at 1. I knew that one, but also they meet at 2. So the limits are 1 and 2. 1 and 2. And I'll save time on this particular video. I'll just say, go ahead and figure that one out. Oh, wait a minute, Weber. Don't leave them in the lurch like that, because look at that first integral. How do I do that one? Oh. Here's what I would do on this problem. I would split it in two pieces. I'd go integral 1 to 2, square root of x minus 1 dx. And then you can say something like minus the integral 1 to 2, and then x minus 1 dx. And that second one is pretty easy, right? But the first one, what does it require? Let u equal x minus 1. Yeah, it does. Du is dx, though, okay? So our integral here becomes integral limits, I'm not going to change, square root of u du. Okay, if you want to keep working on this one, why not? That's really equal to the integral of u to the 1/2 du. So you get 3/2. So I'm going to write 2/3 u to the 3/2 power. And then finally say I've got 2/3. And then the substitution was, in fact, I'll put this in black because we're going back to x, right? So we're going to say 2/3 and then x minus 1 to the 3/2 power. And I'm ready for the limits. Meanwhile, over here, what you've got is minus, when we integrate this guy, we get 1/2 x squared minus x, and we're just waiting the whole time, okay? What you could do is say, why don't we say minus 1/2 x squared, and then minus a minus is plus x, and down here do that, minus 1/2 x squared, and then plus x, and now we apply the limits, which are 1 to 2. Now it gets kind of tricksy, you know. I'm glad I'm doing this problem because we had to do a u substitution. We're actually breaking it into 2 integrals to take care of business here. Really good for you to see how this is done. Too bad you can't ask a question. Raise your hand if you got any questions. But yeah, when I saw this, I go, okay, so I'm going to have to do a u sub on that one. But I know I can separate them out like I did here, and I do that a lot. You know, I show it that way. I actually can do it in my head without really worrying. But you got to be careful because students are like, wait a minute, what'd you just do, kind of thing. Anyway, we apply the limits, and the limits are going to give us what? Let's see. Plugging in 2. So one big old thing. 2/3. Plugging in 2, you got 1. So that's just times 1. I don't care what you say. And then we have minus 1/2 times 1, and then plus 1. That's the top limit. Now here comes... I fell asleep on you. Okay, fell asleep. I got a 1. In the first one, that's 2 minus 1 is 1, but then it becomes minus 1/2, and then it's 2 squared, which is 4, and then plus 2. Sorry. Now we plug in 1. You plug in 1 here, you get 2/3 times 0. He's gone. And then you have a minus 1/2 and plus a 1. Okay, good. We're on track now. So we have, therefore, 2/3. And we have, watch this, we have a minus 2 and a plus 2. Bye-bye, right? I don't know, it just happened. And then we have, that's gone. Then we have a minus is plus 1/2. And then we have minus 1. Okay, so, oh my goodness, what do we have? These are gone. I got 2/3 and 1/2. In terms of sixths, that's 4, 5, that's 7/6 minus 1. Guess what? The answer is 1/6. And it is a small area. Look at that thing. Really a sliver of an area at 1/6 of the square unit. But an area is an area, right? Okay. Areas between curves. I have a couple more. Maybe we can save this for another video. This is getting kind of long. Let's keep going. Let's make it a longish one. Just look at the videos. Okay. So for this one, find the area bounded by the curves. Why? Okay. You always have to look at your work and feel good about it. You just go, you know what? I feel good. Okay, so now to go back here. You should get a sense of satisfaction. I hope that you do when you're doing these problems. Find the area bounded by the curves y equals tan inverse of x. X is 0, y is 1. Now, I set this one up myself. I hope it works. So the picture of it is, as everyone knows, and I'm just kind of wondering if you remember what the tan inverse function looks like. It's the tan function thrown on its side like that. And this is pi over 2 here. And this is a negative pi over 2. Okay, I think I messed this thing up because the tan inverse is also blocked by x is 0 and then y is 1. But I think this should be, change this to pi over 4. That's what I meant to say. I got it backwards. So let's say we go pi over 4 right there. Actually, that's going to be half of u, huh? So this is x is 0, and then this will be pi over 4. Now, you're looking for what region is being bounded by these guys. The answer is right here, okay? So we have an upper curve and we have a lower curve, and a person would say, hey, man, I know my tan inverse stuff. This guy is 1. Tan inverse of 1 is pi over 4 because tangent of pi over 4 is 1. I know we went above your head, some of you. Catch up. Here we go. But here's what the point of this one is this. A person would say, hey, man, the area is the integral from, look, 0 on x to 1 on x, but the area is up here, but that's okay. 0 to 1. We have an upper curve, which is, it's just a straight line. Okay, so I'll say the upper curve is pi over 4, apparently, and then minus the lower curve, which is tan inverse of x dx. And you go, yay, I can do the problem. Except, no, you can't, because we don't know the integral of tan inverse. That's why I did this. We don't know the integral of tan. I don't even know the integral of tan, although I should teach you the integral of tan. That's actually, we can do u substitution for it, but tan inverse, no. So what do? Here's what we do. We don't integrate with respect to x. Instead, we turn it sideways. That's what I wanted to show you. Turn it sideways and integrate with respect to y. That means we have to turn all the functions into, x as a function of y instead of y as a function of x. Okay, we got to change the limits, we got to change everything. So we're going to integrate this way now, which means we're integrating from 0 to this time pi over 4. Okay, cool. Okay. Actually, I get to show you the integral of tan. That's awesome. What an awesome problem, except for I messed up right there. Okay, so the bigger curve, okay, I'm looking at this area. This guy's doing his thing like this. He's doing that. This is pi over 4. This is the 0. This is, the x-axis. And this is the curve. Y is equal to tan inverse of x. And we are integrating. We're slicing up the y. We've never done it before. We're slicing up the y-axis from 0 to pi over 4. Nevertheless, there is a larger function or curve out here, and then there's a smaller one, a lesser one right there. And the smaller one is just 0. So you're really just looking at the area between the tan inverse curve and 0. The farther curve is this way, but I have to write it in terms of y. Okay, because you got these rectangles, and say you pick a y sub I star, you got your delta y, that's the thickness, but then you have to figure out how tall the rectangle is. So there's a delta y, and then there's this, ready for it? Whatever y is, this is the x, horizontal direction. This is x, and it's equal to, turn it around, tangent of y. I have to actually write x in terms of y. But it's worth it because we can do this problem. Otherwise, we can't till we get to Calc 2 anyway. And that's a fun way to look at things. But anyway, the upper curve is just tan of y, and the lower curve is 0. There is no lower curve, but I can write it in if you want me to, and it looks like that. So our problem in this case, integral 0 to pi over 4 of tangent of y dy. And you go, Weber, you're still stuck. You can't integrate tangent. And I say, I get to show you a new thing. Boy, there's a lot of stuff to show you, man. Come on. I have so much to tell you. Here comes some more. Write tangent. Okay, how can you rewrite tangent? In terms of sines and cosines, you remember? That's right. Sine of y over cosine of y. Why is that a big deal? You'll find out. Okay. What are the techniques of integration? There's only one that we've learned. It's called u substitution. Can we use u substitution here? Yes, we can. Look, I'll rewrite it as integral 0 to pi over 4. We've got 1 over cosine of y times sine of y times dy. Okay? The derivative of cosine is minus sine. We got this going on, man. We let u equal, let's put it over here. We let u equal cosine of y, then du, the derivative of cosine, the trick here is it's minus sine y, careful, dy. So therefore, this sine y dy is equal to negative du. And this cosine is going to be replaced with u. Believe it or not. Here we go. So we're getting, okay, you ready? We're getting let's see, we've got integral 1 over u times all of sine y dy is replaced by negative du, which you can write as negative integral 1 over u du, like so. Okay, and what we have there is an answer. We've got it's negative natural log of u. Now I got to watch out for absolute values, but u is positive, I think. Let's find out. You know what I'm going to do? I'm going to really trip you up. I'm going to go let x and y, I'm going to change the limits, man. That's what I'm going to do. I'm going to change it. So u, remember, is cosine of y. The limits are 0 and pi over 4. Cosine of 0 is 1. Cosine of pi over 4 is radical 2 over 2. So my new limits are 1 to radical 2 over 2. Okay, and also here, 1 to radical 2 over 2. All right, I know it's nuts. So therefore, we got to get this guy going on. We've got a negative, I'll put in parens, natural log of radical 2 over 2 minus the natural log of 1, okay, and natural log of 1 is 0. So our final answer is, well, you can do it in different ways. I'm going to play with you because I think this will be the last one I do. I mean, I can talk at the last one, and I'll let you do it. But I got negative, I've got the natural log. In fact, I'm going to write this as 1 over the square root of 2 because it's another name for radical 2 over 2, which is negative natural log of 2 to the negative 1/2. What do the natural logs say to do? You can bring that out as 1/2 because it's going to come out and multiply. Natural log of 2, or how about ln of 2 over 2? Nice answer there to that one, the area between that curve. That was a lot of talking. That was a lot of high-dig stuff. We had to switch it to y to integrate it. Then we had to use sub tangent. No one remembers really the integral of tangent unless you're about to have a test on it. Then some people memorize it. So if we encounter it again, okay, we'll do it. Okay, that's the end of this one. I have one more example. I don't know what I intended to do. If you look at these curves, it's going to be, okay, yeah, one's going like this. That's the parabola. The other one's going like this. All this really is a lesson on, you just write x as a function of y, and you would integrate. Looks like you would integrate, oh, I don't know, wherever it meets. But I'm going to leave that one off. We did enough on this video. See if you can set this guy up. Okay, the area would be the integral. What are the limits, I wonder? The outer curve is what? I don't know. It's y minus 1/2 y squared dy. I'm thinking, again, integrating with respect to y. Okay, the farther curve is the line. The closer curve is the parabola. It's just the limits, man. Where do they meet? We set them equal to each other. You go, y is equal to 1/2 y squared. You'll be able to figure it out. There you go. All right, you guys, that's it for that one. We have one more section, I think. Let's take a peek at that in another video.